Hi, hello everyone. So we're starting into our journey through the wonderful, truly wonderful world of trigonometry. It's at the core, along with algebra, it forms the core of trifecta, I suppose you could call it. Algebra, trigonometry, and calculus. They would form the trifecta, really, of the fundamentals of advanced mathematics. So what we're going to look at today is an unusual concept, but one I think by the end of the video that you'll kind of come to love, and it's the idea of a radian. Now, some of you, if you are doing it, might have come across this concept before. If not, don't worry, I will go through it in enough detail to make sense to you. Okay, so what you'd be familiar with, I suppose, at the moment is the idea of degrees. Okay, so degrees. Okay, and we know that there are 360 degrees in a full circle. The question is, why 360? Why not 100? Why not 300? Why not 1,000? Okay, well, there's a couple of theories as to why it's 360. The one I kind of personally go with is that if you have a big enough circle, you can divide it into 360 segments with enough gap between each segment that it's discernible by the naked eye. Okay, that's one possibility. Okay, the other kind of possibility is that 360 is a multiple of 12, and it's also, more importantly, a multiple of 60. Okay, and 60 is a very important number in mathematics because base 60 is one of the first types of maths. So, you know, it's a very old type of maths, which is the reason why we have 60 minutes, 60 seconds, that type of thing. So that's another reason. But the problem is 360, it was a man, probably a man, could have been a woman, most probably a man who came up with that number. Okay, so it has no basis in reality. It's just an arbitrary number that's been thrown out there. So in order to kind of take humans out of the equation, for want of better words, humans figured out another way of expressing degrees, one that's independent of any arbitrary number. And they came up with the idea of a radian. So what is a radian? I hear you shout, so you're kind of like, well, I want to know what it is. Why is this so cool, right? So a radian, or rad for short, and going forwards, I shall always refer to them as rads, okay? It's a measure of an angle. At the center of a circle, and we are talking about circles here. And this is very important, okay? Subtended. Now, I'll tell you what that word means in a sentence. Equal to the length of a radius. Now, you probably think to yourself, what does that mean? Okay, and I shall show you. Here we have a circle. Here we have the center of the circle. Okay, hope I haven't lost anyone so far. Okay, circle, center of circle. Okay, here is the radius of the circle. Okay, everyone with me so far? That's the radius. Now, this is the important bit. An arc is a line drawn along the circumference. Okay, and most importantly, this arc has the same length as the radius. Okay, so just to put it into context, if this is R and this is L, then R equals L in terms of their distance. Okay, so when I complete this back, this angle in here is 1 radian. So you see how cool this is? Because no matter how big the circle or small the circle, the ratio of R to L is always going to be 1:1, which means that the radian is always going to be the same no matter what size the circle. That's the cool thing about it. Okay, so you take humans out of the equation because circle is a circle. It's a geometrical shape, and you can't lie with it. You can't play around with it. It is what it is. So if the radius is set and the length of the arc is the same as the radius, then the angle created by two lines joined from either end of the arc back to the center, which is 2 radii, is always going to be 1 radian. That is pretty cool, I think. Pretty cool. Okay, so that's not where the fun stops. Okay, because it gets even cooler than that. Okay, so since L is equal to R, okay, and this is the really cool bit. Since L is equal to R, then, and we know that the full circumference is equal to 2 pi R, then how many L's, how many of those are in that? Well, if L is R, then if you divide 2 pi R divided by R, how many of those you actually have 2 pi of them? That's how many radians in one circle. So 2 pi radians is equal to 360 degrees, would you believe? Now, what do I mean when I say 2 pi radians? I mean roughly, and I mean very roughly, 2 pi is roughly 6.28. So there's about 6.3-ish, no, 6.28 radians in one circle. So 6.28 of those segments in every circle in existence. That's crazy, isn't it? Okay, but that means that if I divide both sides by 2, in half a circle, 180 degrees, there's pi radians. There's 3.14 radians in half a circle. So you can actually work out the degrees to the radians and express the radians in terms. And don't worry, you do not have to work this out, because someone somewhere has done a very important job. So this is the time where you get out your log tables, because someone has done it for you. Voila. So 0 degrees is 0 radians. 90 degrees is pi over 2 radians. 180 degrees is pi radians. 270 is 3 pi over 2. 30 is pi over, you get the idea. Okay, someone's worked out the degrees and the radians. Okay, just for you. Okay, which is pretty cool. And even down here, they've written it out. 1 radian is about 57.296 degrees. And 1 degree is round about 0.01745 radians. Why is it roundabout? Because what number are we using to express radians? Pi. And what is pi? An irrational number, which means you cannot express it as a fraction or a decimal. Even though you think you can, you actually can't. Okay, so it's an estimate. So that's what a radian is, which to me is like really cool. Okay, so what can we do with radians? Well, we can do a lot of fun things with radians. Okay, first of all, and before I leave it, to use radians on your calculator, you must change the setup of your calculator. I don't know if you can see, but at the moment my calculator is set to D for degrees. You'll see it on all your Casios. Right at the top, there's a D. You must use your, I can't remember, I think it's like shift function and go down angle unit in my case, and then press 2 for radians type of thing. Okay, it has to be in radians in order for this to work in radians. Otherwise, you could be in trouble and you get a slightly different answer. Okay, so we're going to do one more little cool thing before we kind of have a go at a few of these. Okay, so, and this is where it gets fun, I think, because you're getting into the kind of really cool areas of circles, and I love circles. Okay, not a great circle, but there you go. So let's draw a circle of 1 radian, or sorry, a segment that has a degree of 1 radian. So okay, so we've got 1 radian in there. There's the radius r and the length l. Okay, so what can we be sure? I know that whatever about anything else, that whatever amount of radians that is, it has to be equal to L over R. Okay? So that's just the ratio it has to be. If it was 1 radian, it'd be L over R. If it's 2 radians, it's still going to be whatever, 2L over R. You get the idea? So given whatever it is. So you're going to have to express it like that. So you can actually get the length by just multiplying the radians by the radius. Will give you the length of the arc. So you can rearrange this to find one of the missing pieces of the puzzle. Okay? But the cool thing, okay, is that the area of a full circle is pi r squared. Okay? So if you think about it, and again, you have to kind of think about it a little bit in a bit more detail. Okay? Pi r squared is the full area. What would you need to be able to do to get the area of just a segment? Okay, so let's think about this for a second, because you would have done this in junior cert. So before we in order to get this, let's think of the junior cert. If that was 60 degrees, it goes 60 degrees over the full circle by pi r squared. That would give you the area of that little segment. But we don't have 360 degrees. Okay, we don't have that. But what we do have is this radians over, well, what's the full radians? Full radians is 2 pi, isn't it? We just did that. Multiplied by pi r squared will give me the area of the little sector. So we just made a small little change, and now suddenly you have a formula just for the area of the sector in terms of radians. But I can make this a bit better. If I multiply the top by the top and the bottom by the bottom, I'm going to get theta pi r squared over 2 pi. I can cancel a pi. Okay, so that gives me, if I cancel the pi's, theta r squared over 2, which is the area of the sector. Okay, but that doesn't look nice. Let's take the fraction away. So you can actually write it like this. It's a half the radius by the radians. Half the radius squared by the radians will give you the area of a sector. Okay, now you won't find that in the I don't think you'll find that in the log tables. I'm not 100% sure. I'll just check. No, I'm not seeing it there. Okay, it doesn't matter. You can work it out. It's basically the same as the degrees one you did for the junior cert, except you're just replacing degrees with radians. Okay, so let's give a few a try. So this is where it's going to get exciting. Right, turn 2 pi over 5 into degrees. Okay, so 2 pi over 5 into degrees. Let's think about this for a second. Okay, I can get my, it says pi is 180. So 2 pi is 360 over 5. So what's 360 divided by 5? 72 degrees. Now, next one. Let's try another one. Turn 210 degrees into radians. So let's go backwards. So how do I turn 210 degrees into radians? Well, go back to your reference. I know what pi is equal to 180 degrees. That's true. So what's 210 over 180? That's how many of them there are. So let's see, can that cancel down? 7 over 6. There you go. Converted it back. Okay, we'll try another few. Let's try another one or two. Let's convert 8 pi over 3 into degrees. And we'll convert 230 degrees into radians. Okay, so 8 pi over 3. Well, pi is 180, so that's 8 times 180 over 3. Get your calculator out. 8 times 180 divided by 3 is 480 degrees. That sounds a bit weird, but don't worry. It's okay. You can write down 480 degrees. Okay, 480 degrees is really... That's really 120 degrees. You know what I mean? But you can write it down as 480 degrees. No one's going to argue with you. 230 degrees into radians. Okay, well, we know that 180 is equal to pi. So 230 over 180 pi. Okay, so 230 divided by 180 is, oh god, it's not a nice number. It's 23 over 18 pi. It's not a nice number. Okay, it's not a nice number, but it is what it is. Okay, so that's radians. Radians are cool, they're fun, and you need to be able to use them. Okay, we will try one more. Okay, we will try one more because, you know, why not? Okay, so let's let me think. So that's going to be pi over 4. So you've got pi over 4 is my degrees in there. Okay, and let us say that let's try and figure it out. Let's find the radius of this is 10 centimeters. Okay, so let's first of all, let's find the area of this. So remember from before, the area of the sector is a half r squared theta, where theta is in radians. So that's going to be a half times 10 squared times pi over 4. Now, personally, I always leave these answers in terms of pi because then you don't have to mess around with trying to guess decimal points. So I'm just going to multiply everything but the pi. So that's 100 over 8, which is 25 over 2. So it's 25 pi over 2. So that's the area. And now, the question, I suppose, becomes is that, can you find this? Well, what's our other formula? We know that length is equal to r theta. Okay, so it's equal to r 10 times pi over 4, which is what, 5 over 2 pi. Which is cool. So your area and length, all from the one thing. Okay, right, so that's a little introduction to radians. They're pretty cool. They are what they are, I know, but they are pretty cool. I like them anyway. But your best friend over the next couple of weeks is going to be your log tables. Okay, they really are. They are your best friend. You can't go without them. And I would strongly recommend, if you don't have them, you can download them from the examinations.ie website, or just Google log tables. Okay. Thanks very much. See you next video.